In this video, we're going to cover section 4.5, learning a technique of integration called substitution. So the objective here is to evaluate integrals using the substitution method and then to solve applied problems by using that method. All right, so this is just kind of a review of some basic formulas that we've learned so far. That are going to help with this new method in this section, just to kind of recall things you already know. And they've used the variable u in these examples rather than x, just because when we do a substitution, we're going to change our variable over to the u. So the indefinite integral of u to the power of r du, this is your power rule, add 1 to the power, divide by the higher power, plus c. E to the u, antiderivative is itself, e to the u. 1 over u, antiderivative is the natural log of u, plus the c. Or just the natural log of u without absolute value if you know u is positive. The absolute values are only needed. If u is negative, we are going to assume that u is always positive unless otherwise noted. All right. So this is how it works. So let's say we have the function f of x equals x cubed, and we just want to find dy. So we're going to practice finding values of the derivative of the function just as dy in terms of that differential, because that's part of our process. We're just going to do just that part first before we get into the full problem. All right, so if we have y equals x cubed, this other notation that we learned previously of a derivative, we can write, instead of writing f prime, you could write dy over dx. So dy over dx here would equal 3x squared. Remember, we're differentiating right here, right? Not integrating or not doing an antiderivative. So you'll have to, it's a little bit confusing because you're going to have to do both within this process. So to solve for dy, right, the dy over dx is equal to 3x squared, then the dy would equal, if I multiply both sides of this by the dx, I'd get 3x squared dx. Okay, let's try another one. For u equals x to the 2/3, find du. Okay, so if u is x to the 2/3, du over dx means the derivative. So 2/3 x subtract 1 gives me negative 1/3. So multiplying both sides by dx means du is 2/3 x to the negative 1/3 dx. So it's differentiating the function, calling it the derivative of the function with respect to the variable, and then moving that denominator of that notation to the other side. Okay, here's another one. Y equals e to the x squared, find dy. So dy, derivative of y with respect to x, for this would be e to that power itself times the derivative of the power, which is 2x. So dy would equal, they've just moved the 2x to the front, 2x e to the x, this should be x squared, right? That's a typo, I didn't catch that, I'm sorry, before I printed this out. So 2x is in front, this should be then e to the x squared with the dx on the other side. All right, so the reason that that step is helpful is when I'm evaluating something like this, all right, the indefinite integral 3x squared times the quantity x cubed plus 1 to the 10th dx. If we notice here, this inside function x cubed plus 1, the derivative of it is 3x squared, right? Okay, so we're going to note by looking at the problem that 3x squared is the derivative of this x cubed. So we can, first thing that they do is they take this derivative piece and they just rewrite the problem by putting it back here next to the dx. So just kind of shift it to the back of the problem, x cubed plus 1 to the 10th, and then put the 3x squared back here. So our substitution is going to be, we're going to let u equal this thing on the inside, x cubed plus 1. Then we're going to do like we did on the previous few examples. We're going to find du. Okay, so du over dx would be 3x squared, so then du would be 3x squared dx. Then we're going to rewrite the problem using u. So if this thing was u, this thing becomes u to the 10th, and then all of this stuff, notice, is just simply du. So we're going to rewrite the integral. This was my u to the 10th times the du. So this is a much simpler problem, right, than my original. That's the whole point of a u substitution, to simplify the problem. Okay, so when we get our u to the 11th over 11, our antiderivative plus the c, then we got to go back and put in the original u expression once we're done evaluating. So then after I'm done and got the answer, I put x cubed plus 1 back in for u. So x cubed plus 1 to the 11th over 11 plus c. Okay, this is learning how to work backwards. We've been practicing working backwards this whole chapter. This is working backwards from the chain rule. When you learn the chain rule for finding a derivative, this is how to undo it using antiderivatives. Okay, let's try another one. All right, so if you want to try this one on your own, it's very similar to our last one, or if you want to watch a few more before you try it on your own, that's fine. You can pause the video, try it, and then press play, or you can just watch. So the indefinite integral antiderivative of 4x times 2x squared plus 3 to the third dx. So if we notice that the derivative of this thing on the inside would be 4x, right? It would be 2 times 2 is 4x to the first plus 0. So this thing right here is the derivative of the inner function. Okay, so noting that 4x is the derivative of the 2x squared, right? It's technically the derivative of 2x squared plus 3 because the derivative of 3 is 0. Okay, so we're going to push this to the back like we did before just to see it all together. So we're going to put this first and then put the 4x behind it. So it's next to the dx. Use the substitution, let u be what's inside those parentheses, 2x squared plus 3. Then the du would be 4x to the first plus 0, so 4x, and then the dx, this is du over dx, it would move over here. So this was my u to the third, and then the 4x dx is all that is just the du part. Okay, so now we've got it simplified. Find the antiderivative, u to the 4th over 4 plus c, and then plug back in your u expression to be 2x to the 2nd plus 3. So you get 1/4, 2x squared plus 3 to the 4th plus the c. Okay, so let's try this one. Evaluate the integral 2x dx divided by 1 plus x squared. So this time I can kind of look at this and think, okay, the derivative of 1 plus x squared is 2x. Okay. All right, so when I do my substitution, this time I'm going to let u be the expression whose derivative I see up here. So we're going to let u be 1 plus x squared. When I take its derivative, du, this derivative is 0. This is going to give me 2x dx, which is what's exactly on the top. So we replace the bottom with our u, and then this whole thing on top is our du. So remember, this is like 1 over u du, so that's where we get natural log of u for the antiderivative plus c. Now we're going to reverse it and plug back in our 1 plus x squared for u. So the point here is to make a substitution by looking for some expression whose derivative is also part of the problem. Use your substitution to make a simpler problem. Evaluate the easier problem and then plug everything back in. Okay, so let's try this one. This is very similar to the one we just did. Again, the derivative of the 1 plus x squared is the 2x. So we're going to let u be 1 plus x squared. Then du over dx is 2x and then we move the dx over, so du is 2x dx. So we end up getting here du on top, and on the bottom, this thing is u, but it has a square this time. All right, so when it has a square, a power other than 1, we bring it up to the top and make that power negative. Because this is not going to be a natural log, it's going to be just the power rule. We do our power rule, so we add a 1 that gives me a negative 1, and then I divide by the negative 1, which puts a negative in the front. Add the c, and then rewrite it again, leaving this negative in the front. U to the negative first means I move u to the denominator to make it a positive power, but then they also replaced the u with this expression at the same time. All right, so how about this one? The integral of 6x squared divided by the square root of 3 plus 2x cubed dx. Okay, so if I look at this denominator, what's underneath here, derivative of 3 is 0. This derivative would be 6x squared, which sits right up here. So my choice for u is going to be this whole expression that's sitting underneath this radical. So what they did, so they started by writing the square root as the 1/2 power. That'll be needed to be done eventually. You can do it now or later. We're going to make our substitution like we said. 3 plus 2x cubed will be my u, because du 0 plus 6x squared dx. And we see that 6x squared sitting up here. So when I replace things, this was my u. So on the bottom we have u to the 1/2. This 6x squared dx, all of that is just du. So they put it here. You can put it either on top, or if you put it over to the side, that means just that you have a 1 on the top. We're going to bring up that denominator. So they don't show this, but the next step would be to write this as the integral of u to the negative 1/2, like on the last example. So if that power of u, when I bring it to the numerator, is negative 1/2, we find the antiderivative. So negative 1/2 plus 1 is positive 1/2. So I get u to the 1/2, that's the square root of u. Divided by 1/2 is the same as multiplying by the 2. So that's the right answer, it's just they kind of skipped a little step in there. Then you plug back in your 3 plus 2x cubed from up here to replace the u at the end. All right, how about this one? Antiderivative, natural log of 3x dx divided by x. All right, so this time we want to find an expression for which the derivative is also part of the problem. So this time I'm going to let u equal natural log of 3x. And the reason is because if I take the derivative of natural log of 3x, we would get 1 over 3x, then times the 3, and 3's would cancel. So I get 1 over x dx. Notice here, this is a 1 over an x and a dx. So that 1 over x dx, so both of these things, is this dx over x part, that's my du. So this would become, this whole thing is my u, and then this dx over x, right? All of that stuff is my du. So u du becomes my integral. Power rule for antidifferentiation, u to the second divided by 2 plus the c. Then plug in my u. Natural log of 3x, all of that is squared over the 2 plus the c. So it's kind of like you have to, it's not always the same thing that you have to look for your u assignment. It kind of just depends on the problem. All right, here's another one. The antiderivative of x e to the x squared dx. All right, so on this one, what we're going to do here before we talk about what they wrote here, notice here, this power x squared, its derivative is 2x. right? Well, I have an x here, I just don't have a 2. All right, so when you're missing a constant as part of your derivative, you can adjust for that. All right, so since the derivative of this exponent is 2x, what if I put a 2 here in front? The thing is, if you put a 2 here, you got to also divide by the 2 because you don't want to change the problem, right? Putting the 1/2 in front and the 2 here is like multiplying 1/2 times 2 is a 1, right? So technically those 2's would cancel and it would be equivalent to what we started with, but I'm going to go ahead and put the 2 here because I'm going to need it, which means I also have to have the 1/2 to compensate. All right, so leaving the 1/2 out here, this 2x, we're going to move to the back here next to the dx, just so we can kind of see the 2x dx part all together. Okay, the reason for that is we want to let u be x squared, so du is 2x dx. So the 1/2 is in the front. This was my u, so I'm going to get e to the u, and then all of this stuff is just du. So the antiderivative of e to the u is itself, so the 1/2 stays, antiderivative is itself, plus the c. Now I go back and put in my x squared, which was my u. So sometimes you kind of have to rearrange some things and adjust for what you need. But again, the goal is to try to identify a part of the problem whose derivative is also part of the given function and use that process to simplify it to something easier to evaluate. All right, so let's try this one. Again, notice the derivative of this exponent would be 12x squared. Well, I've got the x squared, I just don't have the 12. So we will compensate for that. We'll put the 12 there because we need it, but when I put the 12 here, I have to adjust by also multiplying by 1 over 12. Okay, oops. So we're going to let u be the exponent. The derivative then is 12x squared should be dx. So this 12x squared dx is the du part, and then this is e to the u, and then the 1/12 still sits in the front. So again, the antiderivative of e to the u is itself, so I get 1/12 e to the u plus c. Then I put back in the 4x cubed. Okay, this one. Integral of dx over x plus 3. All right, so I don't really have much to pick from here, so I'm going to let u be x plus 3. Notice the derivative of x plus 3 is just 1, right? So there really does not need to be anything else involved. So that means it's probably going to work. So let u be x plus 3. So du is just 1 dx, right? So du is equal to dx. So this becomes, since dx is the same as du, and then this bottom is just u. So I get 1, or du over u, which is 1 over u du. So that's a natural log of u. Then I put my u back in. So natural log of x plus 3 plus c. All right. This one we have limits. Okay, it's the same idea to do the problem. We're going to look for something for which the derivative is part of what the other, or the rest of the problem, but then I'm just going to have to evaluate it at the end using my limits instead of adding a c. All right, so the thing under here, x squared plus 3, the derivative is 2x. Okay, well I have a 5x, I don't have a 2x, right? But since the variable's here, I can adjust with my constants. All right, so first we want to find the indefinite integral before we evaluate. All right, so the 5, they just pulled out to the front. And then by noticing that the derivative of x squared plus 3 is 2x, they put a 2 here because we're going to need it, but then we have to divide by the 2 like we've seen in the last couple problems. So if you have a number there, it's just wrong, it's just the wrong number, you can bring it out and then put the number you need there and then divide by that same number to compensate. All right, so they just pushed it back over here again, 2x dx at the end. They changed the square root to the power of a half, leaving the 5 halves in the front. So the substitution is going to be u equals the middle, x squared plus 3. So du is 2x dx, which we've already put back here. So we get the 5 halves stays. This becomes the antiderivative. This is u, so u to the 1/2 du. 5 halves stays. We add 1 to a half, meaning we get 3 halves. Divide by 3 halves means multiply by 2/3 plus the c. So the 2's cancel here, so we get 5/3 in the front by cleaning up those fractions. Remember that my u was x squared plus 3. We put that back in, plus the c. So the only difference is now we have to evaluate from 0 to 1. Now you really don't even need the plus c. You're going to see it cancel out. Remember when we did indefinite integrals before, we didn't worry about that. So if you have it in there, it's fine, but you don't really need it. So evaluate now between 0 and 1. So if I plug in 1, we get this. Minus, then I plug in 0 for x, and I would get this. Notice here, this cleans up to be 5/3, 4 to the 3 halves plus c, minus, this is just 5/3, 3 to the 3 halves, but then the negative distributed, so that's a minus c. So notice my c's just cancel out, so that's why it doesn't matter if you don't put it in there. So then this thing minus this thing on your calculator should be 4.673, and the c's drop out. Okay, so integration by substitution is the reverse of applying the chain rule of differentiation. The substitution is reversed after the integration has been performed. In other words, you put back the original variable at the end, and the results could be checked by differentiating. It's just taking the derivative of the answer in these problems, which I know they didn't show, would involve the chain rule. Okay, this will take some practice. It's a little bit different, and there's a lot of kind of algebra steps involved, but that is the end of section 4.5.